FP1 numerical methods. This is, again, just part of the introduction to this chapter. We're going to look at how to solve a quadratic equation using numerical methods. And we'll look at the three different methods that I mentioned earlier later on in the booklet. But I just want to talk about what we're actually looking for when we're solving an equation. So we've got this equation at the top, and we want to find the roots of the equation. Now, the roots are the places where the quadratic crosses the x-axis. So we're looking for these 2 points, and obviously that varies for each quadratic. So we're after this function f of x being equal to 0, so it's crossing the x-axis. So we're looking for where x squared minus 3x minus 5 equals 0. Now you probably spotted that this doesn't factorise particularly easily, and we know alternative methods by which we could solve this equation. So you're probably wanting to do a quadratic formula at this point, and that would be a good idea. But if this was a cubic or a quartic or a quintic, in other words, these powers were much higher, it would be a lot more difficult to solve. So we've got to look at the principles behind what we would do if we couldn't go ahead with an algebraic method. Now what I'm actually doing here is just looking at the basics of the techniques, and what I've done is I've substituted in 3 values and looked at the answers that I've obtained. So if I substitute in 0, I get an answer of minus 5. If I substitute in minus 1, I get an answer of minus 1. And if I sub in minus 2, I get an answer of 5. Now what that means is that somewhere in between here, somewhere between minus 1 and minus 2, this curve must have crossed through the x-axis. So it's coming up from below, minus 5, minus 1, and then all of a sudden it's got a positive value. So what we're looking for is a sign change. If the values go from negative to positive, we know, because it's a nice continuous curve, there's no gap in the curve, we know that there must have been a cross through the x-axis somewhere between minus 1 and minus 2. What that means is that minus 1 is probably somewhere like this, and minus 2 is like that. So if we see at minus 1, we have a function value of minus 1. And at minus 2, we have a function value of 5. And so we can see that somewhere in between minus 1 and minus 2, we've got a root. So it's that sign change that indicates a root, and that's a sentence that we're going to write very often. A sign change indicates that there is a root in this particular interval. What I want you to do now is pause the video and have a go with some other values other than the ones I've chosen, and I want you to see if you can locate 2 values between which the other root lies. Okay, so if you did try a few other values there, you might have tried 1 and 2 and 3. I tried all those values. I got that f of 3 was minus 5. And then I carried on going along the x-axis, and I got that f of 4 is minus 1. And I kept going, trying integer values. There's no reason why you have to choose integers. You could choose decimals, but we tend to just choose integers. So you'll probably notice that between 4 and 5 is the next root. So 4 will be there, and that gives us a negative value for the function, and 5 is here, and that gives us a positive value for the function. So we've got a root in the interval. There's 2 ways to write this. You can either say somewhere between 4 and 5, which is how you will have written it in C1, but we sometimes also write it like this, like a pair of coordinates. It doesn't mean coordinates, it just means the interval 4 to 5. And we use round brackets to mean that we're not including the endpoints. We know the root isn't 4 and we know the root isn't 5. If we were interested in including the endpoints, you would perhaps put an equals on the inequality, or you would put square brackets to indicate that you might want to include the endpoints of the interval.